All right, this is a super quick talk on PCIe. So basically, on the upper left, you can see that modern day living devices, infrastructure, and compute, everything needs a processor. And at the bottom, you can see the processor sits in a motherboard or a blade, and it fits in a socket. A socket is directly connected to its own memory, so every processor has its own memory. And in a typical multi-socket system, you can connect up to four processors in four sockets without much effort. And this connection is done through UPI. It used to be called QPI or HT for hybrid transport, and now Intel has UPI. If you want an additional fifth socket, called here socket number 4, then extra glue logic needs to be implemented. So every socket processor can talk to a peripheral control hub, and the connection there is through DMI, and this is details that we don't need. But then out of this, then there's this connection from the socket through a, didn't draw this, but through a root complex, and this is a PCI bus. This PCI bus here talks to lots of I/O, and it can talk to other PCIe peripherals that you plug in, USB, SATA, HDMI, DisplayPort, and so forth. And on the upper side here, you can see that a processor uh, directly connects to memory and can connect to GPUs, DPUs, and TPUs through PCIe connections as well. All right, and PCIe has a concept of a connection, and it's called a link. And the link in it can be comprised of one or more lanes. And each lane is a serial connection, and each serial connection has a separate transmit and receive path. For each transmit and receive path, there's actually two signals, called a differential pair. And so basically there's no clock involved, and clock is extracted from the serial data. So this is not a share bus, it's a point-to-point serial connection, which contrasts from the original PCI bus. And in a typical computer architecture system, we have CPU, memory, and I/O, and there are major data paths that can be taken. So let's start with CPU. CPU um, can source transactions to and from memory. We call those load stores. And then CPU can also do I/O reads and writes. The I/O itself can also be a master, and then it could initiate source transactions. It could read and write from memory, and we call that DMA. And then the I/O could also quote unquote talk to CPU. In the olden days, we call this interrupt, and so it sends actually a message over the PCI bus, and so we'll talk more about later on. So major data paths is CPU to memory, which I didn't draw because this is IO-centric. CPU can source transactions to talk to I/O. The I/O can source transactions to talk to CPU, update its registers, and I/O can source transactions and directly access memory. And as we go through the PCIe spec, we're going to start talking about TLP, transaction layer packet. And if you look over here, these are the actual types of transactions that you can have in PCIe. So some of the common ones are memory read lock, memory write, message and message D. And these are ways for IO to interrupt the CPU without actually using a CPU, a physical line. And there's various IO reads and writes, and then also CPU can also configure the IO through configure write, configure read, and there's two types, type 0 and type 1. When you're doing TLP, PCIe, TLP transactions, there's a completion. There's two types of completion: completion with data, which is CPLD, and then completion that doesn't require a data coming back. For instance, you're doing a write, and so that's CPL. Now, PCIe is a layered architecture, and so software requests starting from the top first is handled by the transaction layer, and transaction layer then turns the software request into a TLP packet. The TLP packet then is processed by the data link layer, and more things are added to it on top of the TLP. And then this bag of goodie then is passed to the physical layer, and then finally more stuff is added to it. And so the TLP transaction gets passed through, and more layers are added to it. Now, um, there's also another packet called DLLP, which originates from the data link layer instead of a transaction layer. And so this discerns heavily. A DLLP is not the same as a TLP that got passed through the data link layer and had all these extra data link layer stuff added to it. So DLP originated from the data link layer, TLP originated from the transaction layer, and these two are very different uh, uh, packet types. Um, and then if you look at the TLP, um, there's a header, and then there's a data that's of variable length and optional prefix. When the processor first boots up, it needs to discover what devices are out there in the PCIe world. And so this is called discovery process. And so the CPU will traverse through via the root complex, which is the starting point of all PCIe transactions, and then we'll go depth first. And so we'll look at the left child, go through this entire thing, and then assign this thing called routing ID. Routing ID is a concatenation of a bus number, device number, and function number. Bus and device number is assigned by the software as it traverses through the topology, and function number is already burnt into the device card. The physical to physical communication has low level communication, including ACK and NAC. And also credit communication is done here. The actual tracking of credits is done by the transaction layer. And then also the encoding here is done for Gen 1 and 2. It's 8B, 10B, which means that 10 bits are sent, but then only 8 of them is the real data. Um, from Gen 3 onward, they use a scheme called Scramble and better efficiency. And then in Gen 6, they use PAM, which is 1-for-1. So this is a quick computer architecture talk about memory management unit and then the role of paging, TLB, and swap. So we have a process here, and the process knows about its memory called virtual memory, and process number one, the second process knows about its memory space and its virtual memory. So virtual memory addresses probably will not map directly to physical memory. So this is a range that the operating system assigned to it, and process just deals with the virtual um, address. And so you can see here that the two processes have actually overlapping address, but worry not, the MMU will physically translate them into separate physical memory regions. You're going to hear this a lot. The memory is section partitioned into pages, and later on we're going to hear about paging. So basically, let's see, for instance, process one sends a read to a certain place in memory, so it uses a virtual memory address, and then the MMU translates the physical address, and so it gets remapped from virtual to physical. So when the address virtual memory hits the memory management unit, the first thing that happens is that the virtual address is looked up in the table look aside buffer, which is a hardware implementation of a lookup, and says, hey, you know, does this virtual memory page that you're looking for exist in memory? And if it is, then you just go directly grab it. I'll just help you translate it. But the TLB is a mess that says, hey, I don't know if this memory that's being requested actually lives here. It's not in the TLB. And then so then it gets passed down to the page table, which is implemented software, which is slower. So it does a lookup page, and if it's a miss, that means that this memory, um, this virtual memory doesn't have any corresponding over here, then it might need to fetch the data from disk, and then it's updated. If it is a hit in the cache in the page table, then the translation is that the full physical address is comprised of the new translated page um, prefix and then followed by offset. And so the size of this page will dictate how wide this page part of the physical address is, and then the offset is directly passed over. I know I said that a little fast, but I think you understand it because you've been through this once already. All right, and then so there's this concept of NUMA, non-uniform memory architecture, and basically processors I've shown you earlier wants its own memory, and so these processors have their own memory, um, and sometimes these processors actually want to grab data from the memory of another processor. So for instance, processor 0 wants to read from memory 3, which is located on behind this processor 3. And so what happens then is that, remember those processor to processor connection, um, ultra path interconnect UPI? Well, that request is sent from processor 0 to 1 to 2 to 3, and then information is passed back. So what happens is that processor 0, if it's asking for data from memory 0, it's super fast. If the same processor 0 is asking for data from memory 3, it's super slow, and that makes it non-uniform. So one potential candidate to fix this, quote unquote, is a uniform memory architecture. And so this is simply you take all the memory and then you make it unified, and you go through this big bus, and all of the processors here basically access the same memory. The plus is that you only have one memory. It's probably less complicated to implement. You don't have to do this passing information, looking up stuff. But it's bad because all of these have to probably fight for contention on memory and to slow the system down. So plus and minus. There are constraints in the PCIe world. So when you send out TLP packets, there are constraints about how big the TLP packet can be, and also where it can begin and end. And so if you're starting a read of OX119 from, that's even not even borderline, and so that might be invalid. So basically a read from this address of this length might be broken up into 4 different completions, and that's because there are constraints that need to be adhered to. There's a maximum length of each payload, and then there could be a total restrictions on the entire packet and restrictions on when the boundary crosses a certain boundary, let's say 4K, then the packet will need to be stopped and the restarted for the continuation. So this is the interesting thing about PCIe. So IO here can send interrupts to the processor. Basically, maybe it's received a whole bunch of packets on the Ethernet interface, and now it wants the CPU to read it and process it. So interrupts. Traditionally, interrupts were done through a physical line and line interrupts, and PCIe does support that. But now PCIe officially supports MSI/MSIX, message system interrupt. And so basically here is what happens when IO wants to interrupt the CPU. First, the IO goes onto the PCIe bus, not a physical interrupt, and does a memory write to a certain location in memory. And that still location in memory is special. It's reserved for writing of messages that the CPU will read to see what's up with the interrupt. And so while uh, the PCI write from the IO goes through the root complex, the root complex writes that special interrupt message into the memory and also alerts the CPU that, hey, you need to go here and read the message. The CPU stops what it's doing, comes over, vectors over here, and reads the message, and now knows what uh, probably gets the interrupt service routine vector and goes off and starts processing to interrupt things. And so interrupts are not line driven, rather it's message based. And so this is the one key concept about interrupts in PCIe. So the concept of memory MIO, Ajit stresses is that CPUs um, use memory operations to do both memory and IO operations. So when I was younger at Intel, I remember move and IO instructions. So move being memory and IO being IO. But I guess in the modern world, it's just load store. There's no IO instruction. And so then how do you use load store to access memory versus IO? And the way I think it works is that there is a memory map that says if when you write to the certain region of memory, instead of going to memory, it's now going to go to IO. So that's memory map to IO. All right, so I gave a super quick talk on PCIe. I hope you will listen through this in the future and then just regain knowledge.